In this video, we will discuss flash analog to digital converters. First of all, let us discuss the limitations of previous ADCs. For a n-bit counter type ADC, it will take 2 raised to n number of clock cycles to complete the conversion process. In the case of a counter type ADC with 3-bit output, it requires 2 raised to 3 is equal to 8 clock cycles to complete the conversion process. If counter type ADC takes 2 raised to n clock cycles to convert an analog signal to its digital equivalent, successive approximation register analog to digital converter takes only n clock cycles to digitize the analog signal. This is the block diagram of a flash analog to digital converter. The block diagram of n-bit flash analog to digital converters consists of 2 raised to n number of resistors in the voltage divider network, 2 raised to n number of comparators, and a 2 raised to n is to n priority encoder. So this is the voltage divider network with 2 raised to n number of resistors. This is the comparator network with 2 raised to n number of comparators. And this is the priority encoder with 2 raised to n minus 1 number of input lines and n number of output lines with status output line V. Priority encoder is a digital circuit with 2 raised to n number of input lines, n number of output lines and a status output line. Priority is defined for input lines, and based on the priority of the input, the encoder will generate an output. To understand a priority encoder, we will discuss a 4:2 priority encoder. This is the truth table of a 4:2 priority encoder. There are 4 input lines x3, x2, x1, x0, 2 output lines y1, y0, and a status output line valid. The first row, when x3 is equal to 1, irrespective of the logic values at the other 3 input lines, y1 is equal to 1, y0 is equal to 1, and valid is also equal to 1. And if none of the 4 input lines are high, then y1 is equal to y0 is equal to 0, and valid output is also equal to 0, as shown in the last row of the truth table. Now we will discuss the working of a n-bit flash ADC. The voltage divider network consists of 2 raised to n number of resistors, which divides the reference voltage into 2 raised to n equal values. The inverting inputs of 2 raised to n comparators are connected to the junctions of resistors in the voltage divider network. Analog input voltage, which should be digitized, is applied to the non-inverting input of all the comparators in the circuit. Output of all comparators are applied to the 2 raised to n input lines of the priority encoder. The priority encoder will convert the value at its input to a binary number which is equal to the digital equivalent of the analog voltage applied. For analog input voltage greater than 0, status signal V will be high, else low. For simplicity, let us consider the diagram of a 2-bit flash analog to digital converter. So this is the diagram of a 2-bit flash analog to digital converter. The diagram consists of a voltage divider network with 4 resistors of equal value and reference voltage is VR. The comparator network with 4 comparators and a priority encoder with 4 input lines, 2 output lines and a status line. The following steps which we are going to discuss are not sequential but simultaneous. Resolution is selected as 1 volt, so reference voltage is 4 volt in this case. Voltage at the inverting inputs of comparators are 0, 1, 2 and 3. Let analog input voltage is VA is equal to 2.85 volt. For the last comparator, differential input voltage is equal to 2.85 at the non-inverting input minus 0 at the inverting input. So differential input voltage is positive, so output voltage is high. Similarly, for the next comparator also, differential input voltage is positive, output voltage is high. For the next one also, differential input voltage is positive, so output voltage is high. For the topmost comparator, differential input voltage is equal to 2.85 minus 3. Differential input voltage is negative, so output voltage is equal to 0. So for the priority encoder, x3 is equal to 0 and x2 is equal to 1. So irrespective of the logic values at x1 and x0, output of the priority encoder will be y0 is equal to 0, y1 is equal to 1, valid is also equal to 1. So y1, y0 is equal to 1, 0, which is the digital equivalent of x2. So if analog input voltage is equal to 3.5 volt, in this case, differential input voltage of all the 4 comparators is positive. So output voltage is logic 1. So y1 is equal to 1, y0 is equal to 1, valid is also equal to 1. This is the block diagram of a 3-bit flash analog to digital converter. Consists of a potential divider network with 8 resistors and reference voltage is equal to 8 volt if resolution is equal to 1 volt. There are 8 comparators and a 8:3 priority encoder with 8 input lines, 3 output lines and 1 valid output line. Advantages and limitations of flash ADC. The prime advantage of flash ADC is its speed of conversion. As soon as an input signal is applied, its digital value will be available at the output of flash ADC, and other analog to digital converters lack this advantage. The major drawback of flash ADC is its complexity. For a 2-bit flash ADC, we need a voltage divider network with 2 raised to n number of resistors, 2 raised to n number of comparators, and a 2 raised to n is to n priority encoder. We found that for a 2-bit flash analog to digital converter, the circuit consists of 4 comparators and a 4:2 priority encoder. In the case of a 3-bit flash analog to digital converter, the circuit consists of 8 number of comparators and a 8:3 priority encoder. So we can say that the number of comparators will be doubled if number of output bits is increased by 1. Thanks for watching Circuits Analytica. Enjoy learning.